Speaking of charts, I hope you took a printout of the one I sent, maybe on Saturday probably or Sunday. You will need multiple printouts, because if you mark it, you can't use it in the exam. You have to bring a fresh one to the exam or the quiz. You will require it during the quizzes. I am referring to the chart. Of course, the same instruction holds for tables also. If it is marked, you can't use it in the exam. So, you will need one unmarked copy dedicated to that purpose, and you will need it for the quizzes as well as mid semester and final. Mid semester, I was told, is on 21st September. I am sure you will keep checking. So, energy equation, the version we have studied incorporates the first law of thermodynamics as well as the second law. For a flow process. So, the material is essentially stagnant, then you might have seen versions like Q minus W is equal to delta U, where U is internal energy. In a flow process, you deal with rates of heat transfer, rates of work transfer, and changes in the total energy. So, the form that is applicable for our discussion follows from Reynolds transport theorem, where the left hand side is written as Q dot minus W dot. So, this is a general form. By the way, I should mention that our analysis is at the global level. That is how we start with a control volume. Slowly we will transit to local analysis, but for your quiz number 2, we will restrict our attention to global analysis, mass, momentum and energy equations, global, which means you start with a control volume. Now, do not show the control volume with the solid surface. So, you extract the control volume, carry out all the analysis. It is just to maintain continuity with your free body diagram kind of mindset. So, once you become very familiar, of course, you may show reactions, this, that, all within the assembly, but it always helps if you can identify the component that is being analyzed and show the forces acting on it. So, this is a general version, but we are going to specialize to a class of problems. So, we are going to assume now a very large number of problems are unsteady, but since we are just introducing the subject to the class, let us restrict attention to steady flow. Now, the original equation can deal with unsteadiness. The integral also can be evaluated as the average value of the integrand multiplied by volume. How do you estimate a derivative? It is like a typical change in the variable divided by a time scale over which the evolution has taken place. So, these are approximations. We are not solving an integral equation, but really speaking that is what it is. But we are approximating terms to algebraic form, so that we just have to evaluate algebraic equations. But essentially, you have three equations: mass, momentum, energy. So, these are coupled, and then by substituting one in the other, we do decoupling of those equations. But in principle, you have a coupled system. So, the moment you say steady, the right hand side, the first integral on the right hand side is 0. And let us also stipulate the fluid medium to be incompressible. So, accordingly, we are thinking of liquids by and large, but gases also behave as incompressible under a wide range of conditions. We will see what those conditions are a little later. So, then q dot minus w dot is rho integral over C s E u dot n ds. So, you might be familiar with the first law analysis up to this point. So, some of you might have done a second course on thermodynamics, others might not. In any case, our book has some introduction. So, we do not have an opportunity to get into the details of thermodynamics. But you can imagine, let us say, flow through a tube. On the left hand side, there is some pressure P 1, right hand side is some pressure P 2. So, a fluid element will have to be pressurized to P 1, so it flows into the tube. Okay. Now, if P 2 is greater than atmospheric, there is some work exchange, that fluid is coming out at pressure P 2 and then joining the ambient. So, there is some amount of work exchange on that boundary also. So, these contributions you might recall from your earlier courses. These are all called a PDV kind of work. So, in the flow process, it is called flow work. Okay. So, within your control volume, well, specifically at the control surface, you will have PDV kind of work exchange called flow work. And then there could be a device inside, like a propeller or a pump or a turbine. The word pump is used when you are dealing with liquids. Terms like propellers, for example, are used when the working medium is gas. Similarly, the word compressor also implies generally a gaseous medium. So, this W is equal to W s plus W f, and okay, what was E? E is called total energy, which has a thermal component, a kinetic energy component and a potential component, potential energy component, which in our discussion will be gravitational. So, as you go further up in the subject, you can deal with electric fields, chemical potential and so on. All of them can be added to small e, total energy. So, this PDV works. So, can be assimilated in the definition of total energy as, if you write E as I plus P over rho plus U square over 2 plus G z, then first law of thermodynamics you can transfer W f to the right hand side. I think in the previous lecture, this original E was shown with a tilde. And then when you modify the definition of total energy to include pressure, then we give it a symbol E. Just repeating the symbols of last time. So, E tilde becomes E when the flow work is absorbed in the definition of total energy. Okay, this is certainly a form of the energy equation based on first law of thermodynamics. Now, to carry out fluid flow calculations, later in this course we will do heat transfer calculations, where temperature is allowed to change from point to point, like a velocity distribution, pressure distribution. You will also have a temperature distribution. You may have a hot object that is cooling in air, or you may have a quenching process, or you may have high temperature outside, low temperature inside, and energy, thermal energy is coming through the walls of the room. So, you will have problems of this type, where temperature is not constant. In the initial part of the course, let us require the medium to be isothermal. So, here we note that for a pure substance, I will be a function of P and T, but because it is incompressible, it is only a function of T, and now we require it to be isothermal. That means there is no change in I during the flow process. Everywhere temperature is constant. I think somebody asked quite correctly, I is not 0, but it is constant. If it is constant, then its integration on Cs, here you replace E by I, and this U dot n is 0. I is constant. That means the right hand side will not have any contribution from I, okay, if I is constant. So, it is almost like atmospheric pressure acting as datum and cancelling off. Okay, so, if the flow process is isothermal, then you do not have to carry I with you, and we redefine E as P over rho plus U square over 2 plus G z. Now, strictly speaking, this U should be written as vector U, but in most of the problems we are talking about this unidirectional flow. So, that velocity is, otherwise it is U vector U square. So, probably I should show vector U in the original definition and then here. So, this is flow work and then isothermal. These are specialization that will enable us to carry out fluid flow analysis. So, by looking at examples, then you will know the utility of these approximations. If in your problem the approximations do not hold, then you have to go back to the original form. It is not that you are compelled to make these approximations, but to illustrate the utility of the subject, we make some approximations and solve some problems. One important consequence of making the flow isothermal is on Q dot. So, in the previous class we talked about how natural processes tend to be dissipating, irreversible. There is always friction. In the case of fluid flow, again we try to recall the original experiment of Newton, which reveals that there is a property called viscosity, which plays the role of internal friction in the fluid. And if you are going to set the fluid in motion, then velocity gradients are set up because one fluid layer is trying to retard the other, and the retardation is a maximum at the solid wall, where the wall really holds that fluid particle at rest. Okay. So, elsewhere fluid is moving, at the wall it is stationary, and you have a velocity gradient set up. This gradient permits internal friction to come into picture. It's almost like one solid surface sliding on another, giving rise to internal dissipation within the medium. Okay. So, if that is the case, then this dissipation, internal dissipation will get converted into thermal energy of the fluid, and its temperature will try to go up. But then if you insist the temperature is constant, then it means that you are providing, let us say, some kind of active cooling to the medium, and then you are taking that the heating effect is being transferred to the environment. So, if the process is isothermal, Q dot has to be from within to the environment. Now, in a way, this entire discussion, the presence of internal dissipation, which is also called viscous dissipation, because viscosity is at the origin, is at the root of all the conversion of kinetic energy to internal dissipation, internal energy of the medium, which is then transferred to the ambient. So, Q dot is not 0, in fact Q dot is less than 0. So, a necessary consequence of the medium being isothermal is that Q dot is less than 0. Okay. So, here you have to recall this sign notation, that heat added to the control volume is positive and work extracted out of the control volume, like a turbine, let us say, is positive. And of course, the converse would be negative. Okay, so now saying something is negative does not help in carrying out calculations. So, we will see, but let us look at the consequences which apply mass, momentum and energy equations with the result we have obtained so far. Now, I think that should explain why so q dot minus w dot s equal to rho integral C s E u dot n d s with q dot less than 0 is a statement of the first and the second laws of thermodynamics. Okay. Now, let us look at the utility of these equations through examples. So, let us take the familiar example. I think in the previous class we studied an example of flow past an object, which gave us the result that if q dot is less than 0, then force acting on the control volume is to the left, there is fluid leaving the side boundaries, force acting on the object is to the right, and there will be a velocity deficit. So, all these results followed. So, let us go back to a simple example of flow through a tube. So, this is plane 1, this is plane 2. So, set up a control volume like this and pick the side wall, the side surface to overlap the tube wall, so that u dot n is 0, and then this is an example of flow through a tube. Of circular cross section, which is why we just show a surface 3, which is the side, the circular part of the tube. So, let us write the mass, momentum, and energy equations. So, minus u 1 a 1 plus u 2 a 2 equal to 0, and of course, a 1 is equal to a 2. For momentum is equal to rho minus u 1 square a 1 plus u 2 square a 2, which is 0, and it is also equal to P 1 minus P 2 a 1 area A. So, this is cross sectional area A plus tau wall 2 pi r L. Which is 0, and for energy equation we have q dot equal to rho, if you remember, it was E times u dot n. So, minus u 1 a 1 E 1 plus u 2 a 2 E 2, which is you can take u 1 a 1 out, rho u 1 a 1 is m dot times E 2 minus E 1 less than 0. This is the energy equation, because q dot is less than 0, where E is p over rho plus u square over 2 plus g z. So, I am just writing out more details than necessary, because it is the very first problem that we are looking at. So, So, if you say that the tube is horizontal, then there is really no change in z, no change in z. How about u? U is also constant, no change in u. So, when you say E 2 minus E 1, it is equal to P 2 minus P 1. So, P 2 is less than P 1. So, I think in the previous class we had argued just based on momentum equation that the wall is going to retard the flow. Therefore, the sign of tau wall should be negative, but that you are able to derive based on the first and the second laws of thermodynamics. Together we call the set to be the energy equation. So, P 2 minus P 1 is less than 0. So, if you substitute in the momentum equation, it will tell you P 1 minus P 2 is positive, therefore, tau wall is negative. So, on the control volume, so this is negative, that means on the control volume you will show the shear stress acting at the wall at the boundary of the control volume in the negative direction. Now, the question is how much is P 2 minus P 1? That calculation we will take up as we go along, because it is not adequate to say, well, P 2 minus P 1 is less than 0. So, you want numbers, but at least based on the initial formulation, this is the result we have. So, this such problems where you have one inlet and one exit, so single inlet, single exit problems. Okay. And if you can have multiple inlets and multiple exits, that is a generalization, but it is no big deal, because your integral then will be summed over all the inlets and sum over all the exits. Okay. But you can't just pick one inlet out of that entire collection and one exit out of the other collection. You have to sum them all up. Okay. So, this is an example of single exit problem. So, you see that q dot is equal to m dot E 2 minus E 1. So, this quantity q dot divided by m dot appears often in calculations, and the units, so it is given a symbol small q. Okay. Similarly, the shaft work per unit mass flow rate, okay, it is given a symbol small w s, and these will have units of E, which is meter per second whole square. And what are the units of capital Q? Those would be in watts. So, please convince yourself that these are the units. Now, this q dot arises from internal dissipation and things like that, and it shows this equation q dot equal to m dot E 2 minus E 1. It shows that your total energy is lost within the tube. But then what about conservation of energy? It is lost in the sense that the sum of P u and gravity is getting converted to thermal. Okay. The conversion is into thermal, but as far as you may call it the mechanical component of total energy. So, So, you can think of total energy as mechanical plus thermal. So, thermal is constant. So, that much. So, this part, mechanical part, is diminishing in the flow direction. Okay. So, from that angle, this q dot is referred to as a loss, energy loss. So, you should not say energy is lost and conservation of energy principle is violated. It is not, because it is getting converted to thermal, but the mechanical part of it is lost in the flow direction. Now, you can see, compare this P 2 minus P 1 here appearing in the energy equation with P 1 minus P 2 appearing in the momentum equation. Okay, and the momentum equation now tells you that the loss is because of shear stresses acting on the fluid, and these shear stresses scale with viscosity. So, this internal dissipation is viscous in origin. So, it's so, when two solid surfaces rub against each other, there is a natural friction. Okay. So, if you look at it very closely, it could be because of small roughness elements on those surfaces, which is the origin of that friction. Friction can also be chemical in origin. So, in terms of viscosity, of course, you do not have roughness elements, but you have a particulate motion, which then creates, which is the origin of this internal friction. We may have a chance later to discuss how exactly viscosity converts mechanical energy into thermal energy. So, that we look at later. For the time being, on the global scale, shear stresses are the cause for energy loss. So, that you can understand by looking at the momentum equation and the energy equation. Now, one more interpretation is flow. Well, if flow takes place from left to right, pressure will decrease from left to right. So, flow takes place in the direction of decreasing pressure. This is a very loose kind of a statement, which we see is valid for a tube of constant circular cross section. Indeed, pressure decreases in the direction of flow. So, let us look at an extension of this problem. This is flow through a diffuser. A diffuser is like a tube whose area of cross section increases in the flow direction, like that, a conical diffuser. Okay. You can also have a planar diffuser or a diffuser with a rectangular cross section. In every case, area increases in the direction of flow. So, if you write the mass, momentum and energy equations here, which I will do quickly now, minus u 1 u a 1 plus u 2 a 2 equal to 0, f x equal to minus rho, I am sorry, is equal to rho minus u 1 square a 1 plus u 2 square a 2, but u 1 a 1 is equal to u 2 a 2. So, you can write this as m dot u 2 minus u 1. Okay. And applying the energy equation, q dot is equal to rho minus u 1 E 1 A 1 plus u 2 E 2 A 2, which is m dot. M dot is rho u1 a1. Is also equal to rho u2 a2. Okay, so since a2 is greater than a1, it follows that u2 is less than u1. So, now let us expand E2 minus E1 in terms of its components. Components are pressure, velocity and gravity. Now, thinking of a horizontal configuration of the diffuser. So, there is no change in gravity. Gravity, that means the gravity coordinate. So, this will be m dot u2 square over 2 plus, well, I should put pressure first. So, okay, so this can be written as since it is an inequality, m dot is positive. So, it can be dropped. So, P 2 minus P 1 over rho will be less than, you can take these two u 1 square and but u1 is greater than u2. So, the right hand side is not 0, but some positive quantity. So, that means P2 minus P1 can be positive in this geometry. What does it mean? Flow is from 1 to 2. So, as flow goes from 1 to 2, pressure can actually increase in this geometry depending on the area ratio. That means, depending on how much u1 exceeds u2. So, here is an example where flow is taking place in the direction of increasing pressure. So, I just want to dispel the misunderstanding that flow will always take place in the direction of decreasing pressure. Flow will always take place in the direction of decreasing total energy, right? E2 minus E1 less than 0. When flow is from 1 to 2, where 1 is the inlet plane, 2 is the exit plane. Okay. So, flow is from 1 to 2, all you can say is E 2 will be less than E 1, and then depending on other circumstances you can conclude maybe pressure will decrease, pressure will increase. So, here is an example. In a diffuser, flow takes place in the direction of increasing pressure. Okay, but the total energy of the fluid will diminish in the flow direction. Whatever be the situation, it is going to diminish. So, let us look at example of a pump. So, in a pump the shaft work is not 0. So, is it positive or negative? Shaft work, when you substitute positive negative from the viewpoint of the energy equation. Huh? Huh? Shaft work? You know, if it is work output from the device, it is positive. So, here it is a work consuming device, right. You have to plug it in, it is going to consume electricity, and therefore, it is the shaft work is negative. So, the way to do these problems is write the energy equation, and then when you substitute for shaft work, put a negative sign. Okay. So, the configuration is, let us say, just a pump. So, a pump is connected to some tubes, and this is inlet, this is exit. So, see these minor details, it is all just notation. Okay. You can see that the exit tube is kept a little above the inlet tube. For a turbine, we reverse the two. So, let us say these segments are all very short. I forgot to mention that these losses in a tube, we linked it to tau wall. Let us look at this. See, we linked losses to tau wall, but it was also proportional to tau wall had viscosity in it, and you can see it is also proportional to length L. So, we expect losses to be small if the tube length is small. Okay. So, let us write the energy equation between points 1 and 2. So, Q dot minus W dot shaft work is equal to m dot E 2 minus E 1. So, this is the energy equation. So, we have a steady flow process, that means the pump is in continuous operation. Okay, the steady flow going through the pump. So, let us assume that the pump is 100% efficient. So, let us say it is loss free, and then there are no losses in the connecting tubes. So, here in this little example, Q dot is 0. So, these are components, you can think of components in a hydraulic system. So, we will take up the analysis of a hydraulic system a little later. So, in that system you will have pumps, turbines, tubes, many other valves, many other components. Just analyzing them, we just analyzed a tube, E 2 minus E 1 less than 0, that is the energy equation. Okay. And that E 2 minus E 1 taking place in a tube is also referred as the loss taking place in the tube. Is the energy loss in the tube. So, now the tube lengths are small. So, there is no loss in the tubes, pump is taken to be 100% efficient. So, there are no losses inside the pump. So, we have 0, and let us write this. So, just with reference to this sign convention. This minus W s can be written as plus capital W p, P for pump. Okay. And now, W p is a positive quantity, is equal to m dot E 2 minus E 1, and so E 2 minus E 1 is equal to small W p. Okay. Small W p is capital W p divided by m dot, which is greater than 0. So, now, let us say Z 2 equal to Z 1. Let us say the tube diameters are equal. U2 is equal to U1. So, the only change that is happening in the fluid, which in this case because of the incompressibility condition, and we are just talking about pumping of water, pumping of oil, pumping of liquids in general. So, P 2 minus P 1 over rho is greater than 0. Okay. So, the effect of a pump is to raise the pressure of the liquid or the fluid in general, liquid in particular. Okay. So, across the pump there is an increase in pressure. Okay. So, if you do the same analysis for a turbine, this is point 1, point 2, this is the flow direction. You will get E 2 minus E 1, which is P 2 minus P 1 over rho will be equal to minus W t less than 0. Okay. W t is the change in sign, and W t is a positive quantity. So, it is like power consumed by a pump. You do not say power consumed by a pump is minus 300 kilowatts. You do not talk that way. You just say power consumed by the pump is 300 kilowatts, and when you substitute in the equation, you take care of the sign. Similarly, the power output of a turbine is 100 kilowatts. Okay. So, but when you substitute in the equation, it is with the sign taken into account. So, you can see that pressure will decrease in the direction of flow across the turbine. So, I think I had some example here. So, let us take a look, since I keep talking about pumping water from the ground floor to the roof of your hostel. Let us take that example. So, this is 1. This is 2. Vertical or horizontal, we will have the same equation E 2 minus E 1 less than 0. Okay. Now, later of course, the flow cannot happen on its own, you have to connect it to a pump. So, a pump with a vertical tube. So, that example we will see later. So, here E 2 minus E 1 less than 0, but you cannot conclude that P 2 minus P 1 is less than 0, because there is a change in the gravitational head. So, P 2 minus P 1 over rho plus G Z 2 minus Z 1 will be equal to 0, will be less than 0. Okay. This is the governing equation for a vertical tube. So, in the next class, we will talk about a tube connected to a pump, okay. And we will look at hydraulic systems in general, where you have an assembly of all these components and set up the mass, momentum, energy equations as appropriate. Sometimes you need only the energy equation, sometimes you need only the mass balance equation, but as appropriate we set up those equations. Okay. After that, we look at examples where losses can be quantified. It is not enough to say q dot less than 0, you want some numbers. So, we start talking about numerical values for the losses. If you have any quick comment, I was planning to have a discussion hour of my own on Saturday, but Saturday something else has come up. You have discussions and problem solving happening in the tutorials. So let's say, of course, I don't know if this room is available, but do you have a class from let's say 6 to 7 on Friday? No class? Let's see if possible, but it's not a problem solving session. It is not, I will not write anything, because then you may ask what is the purpose. So we'll see, some purpose may emerge. So if that happens, I will let you know on email. Of course, we'll meet on Wednesday also. We'll carry on.
I didn't understand the sign convention. Was then my